There's a hidden weakness inside modern timber structures that, honestly, most builders never even question. Every timber structure built outdoors today carries a quiet contradiction, buried deep inside its frame. If you walk across a wooden footbridge in a park, maybe take a look at the deck of a backyard pergola, or inspect the beams of a lakeside dock, you'll almost always spot the same design repeated thousands of times. Wood held together by steel. Bolts, screws and nails are driven into timber with the assumption that metal means strength, permanence and reliability. Yet history has shown us something rather uncomfortable. The steel that promises strength often becomes the very mechanism that, well, destroys the wood surrounding it. The final siren, as it were, sounds not from outside, but from within. Engineers have known for generations that when steel penetrates outdoor timber, it introduces a chemical and structural conflict that, frankly, never truly resolves itself. Steel rusts. Wood absorbs moisture. When these two materials interact under changing weather conditions, corrosion begins slowly and silently. Rust expands inside the wood fibres, trapping moisture and opening pathways for decay. Over time, what once looked like a strong joint becomes a hidden pocket of rot, spreading outward from the metal core like a disease. Many historic builders actually understood this problem long before modern construction manuals were ever written. 19th-century carpenters, for instance, frequently avoided metal hardware entirely when building timber bridges, barns and long-span structures. Instead, they relied on wooden pegs, complex joinery, and what was often called all-wood construction. Structures built under that philosophy, well, sometimes survive for centuries with remarkably little internal decay. In this documentary guide, we'll examine why modern fasteners frequently fail in outdoor timber structures, how rust becomes the catalyst for internal rot, and why older woodworking traditions may, in fact, offer the most durable solutions available even in the year 2026. Along the way, we'll look at real engineering failures, explore the chemistry behind rust expansion, and consider practical ways builders and homesteaders can apply historic knowledge to modern structures. This subject, you see, sits right at the intersection of history, engineering and survival craftsmanship. For anyone who cares about durability, long-term construction or the hidden weaknesses inside modern building practices, understanding this story really does change the way you look at every nail and bolt driven into wood. It's all about understanding why steel and wood behave like uneasy partners outdoors. At first glance, steel and wood seem, well, perfectly compatible. Steel provides tensile strength, while wood offers compressive strength and structural flexibility. When builders combine the two materials, the result appears to be a reinforced system where each component compensates for the other's weaknesses. The problem, though, begins with the environment. Outdoor timber structures exist in a constant cycle of wetting and drying. Rainwater penetrates surface fibres. Morning dew condenses in microscopic pores. Sunlight then drives moisture back out, expanding and contracting the wood in subtle daily movements. These cycles are harmless to solid wood that's allowed to breathe and dry naturally. But the moment steel is introduced into the interior of that timber, the moisture cycle changes. Steel fasteners trap water. Every nail hole or bolt channel becomes a miniature cavity where moisture lingers longer than it would on open wood surfaces. Once water sits against steel long enough, corrosion begins. The chemical reaction between iron, oxygen and water produces iron oxide, more commonly known as rust. Now, rust does not behave like the original metal. Iron oxide expands significantly compared with the steel that produced it. As corrosion grows, the expanding rust presses outward against surrounding wood fibres. This expansion creates microscopic fractures within the timber. Those fractures, well, they hold more moisture. The process becomes a self-reinforcing cycle. Rust creates cracks. Cracks hold water. Water accelerates corrosion. Eventually, the surrounding wood softens and begins to decay. Carpenters sometimes describe this as rot radiating outward from a nail or bolt. In many cases, the timber looks healthy from the outside, while the interior has already been compromised. Modern construction often assumes that metal hardware adds strength indefinitely. But actually, the strength of the joint slowly declines once corrosion begins. What rust expansion physically destroys wood fibres from the inside. Rust is not simply discoloration on metal. It is a mineral structure that grows in volume as the corrosion reaction progresses. Engineers sometimes compare it to a wedge slowly driven into surrounding material. When a steel bolt buried in timber begins to rust, the expansion occurs along the entire surface of the metal. The rust pushes outward against the surrounding wood, separating the fibres that once gripped the bolt tightly. As the wood fibres separate, the mechanical grip of the fastener weakens. The joint begins to loosen. But the damage does not stop there. Separated fibres create pathways where fungal spores can settle. Wood decay fungi thrive in environments where moisture remains trapped and oxygen is available. Rust-fractured wood becomes an ideal habitat. Over time, the wood surrounding the fastener turns darker and softer as fungal activity begins breaking down cellulose structures. At that stage, the damage often spreads beyond the immediate fastener location into surrounding structural members. Many bridge inspections reveal precisely this pattern. The steel bolt remains intact, while the wood around it has become soft and degraded. In extreme cases, the bolt can be pulled free with little resistance because the surrounding timber has lost structural integrity. What originally served as reinforcement becomes a point of structural failure. Historic timber bridge failures reveal how metal hardware accelerates decay. The history of timber bridge engineering provides some of the clearest examples of how metal fasteners can unintentionally accelerate structural failure. During the 19th century, many rural bridges were constructed almost entirely from timber using mortise and tenon joints secured with wooden pegs. These bridges sometimes lasted many decades with minimal maintenance. As industrial steel production expanded in the late 19th and early 20th centuries, engineers began replacing wooden joinery with metal bolts and plates. The goal was efficiency and strength. Steel connectors allowed faster assembly and simplified structural calculations. However, long-term inspection records began revealing a troubling pattern. Timber structures, reinforced with steel hardware, frequently developed rot around bolt locations much earlier than expected. One widely discussed example occurred in the collapse of the Big Bayou Connaught Railroad Bridge after severe structural weakening following a marine collision. Investigations highlighted how structural connections between metal components and timber members were vulnerable to moisture retention and corrosion. While the disaster involved multiple factors, the interaction between steel hardware and wood was part of the structural vulnerability chain. Similar inspection findings have been reported in covered bridges throughout North America and Europe. In many restoration projects, engineers discovered that original wooden joints remained solid, while later metal reinforcements had created rot pockets around bolt holes. The pattern is consistent. Wherever steel penetrates outdoor timber, corrosion eventually appears. Wherever corrosion expands inside wood, decay soon follows. 19th century carpenters often preferred wood joinery for durability. Long before corrosion science was formally studied, experienced carpenters recognized that wooden joints weathered outdoor environments differently than metal fasteners. Many builders in the 19th century favored complex joinery systems such as mortise and tenon connections, scarf joints, and interlocking beam structures. These joints were typically secured with hardwood pegs known as trunnels, a term derived from tree nails. A trunnel was carved from dense hardwood and driven through aligned holes in adjoining beams. Once installed, the wooden peg expanded slightly as it absorbed moisture, locking the joint tightly. Unlike steel fasteners, wooden pegs moved with the surrounding timber as humidity changed. Because the materials shared similar expansion properties, internal stress remained low. Even more important, wooden pegs did not introduce corrosion into the joint. Moisture entering the connection could eventually evaporate rather than being trapped around rusting metal. Historic covered bridges demonstrate how effective this philosophy could be. Many structures built in the early 19th century continue to stand today after more than a century of exposure. One famous example is the Cornish-Windsor covered bridge, one of the longest wooden covered bridges in the world. The structure relies heavily on timber joinery techniques developed before widespread steel fasteners became common. The durability of such bridges often surprises modern engineers who expect wood structures to decay quickly. The secret lies partly in eliminating metal components that would otherwise trap moisture and initiate root growth. Why is the philosophy of all wood construction being reconsidered today? In an era dominated by industrial materials, the idea of building large structures entirely from wood might sound outdated. Yet a growing number of engineers and restoration specialists are revisiting historical timber techniques with renewed interest. One reason is longevity. When wood members are joined using traditional carpentry methods, the resulting structure can last far longer than assemblies dependent on metal fasteners. The absence of corrosion eliminates one of the primary triggers for internal decay. Another advantage is maintenance simplicity. If a wooden peg begins to degrade after many decades, it can be replaced easily without introducing rust. The joint remains compatible with surrounding materials. Environmental sustainability also plays a role. Timber joinery reduces reliance on steel manufacturing, which carries a significant carbon footprint. But perhaps the most compelling reason lies in resilience. Structures built using compatible materials often adapt better to environmental stress over time. Wood expands and contracts with humidity. When every component of the joint shares that property, the structure behaves as a unified system rather than a combination of conflicting materials. This philosophy resonates strongly with survivalists, homesteaders, and traditional craftsmen who value durability measured in generations rather than decades. Applying historical joinery principles in modern outdoor construction, understanding the weaknesses of steel fasteners does not require abandoning modern construction entirely. Instead, it opens the door to smarter design choices that combine historical knowledge with contemporary building techniques. Consider a simple example. Constructing a backyard pergola intended to last for many decades. A modern builder might instinctively assemble the structure using galvanized lag bolts or structural screws. While these fasteners provide immediate strength, they also introduce potential corrosion points within the timber. An alternative approach involves using traditional joinery. Posts can be connected to beams using mortise and tenon joints, where a protruding tenon from one beam fits into a carved cavity in another. The joint is then secured with hardwood pegs. To create such a joint, the builder first measures and marks the beam where the tenon will be cut. A saw and chisel remove material until a rectangular projection remains. The receiving beam is then chiseled to create a mortise cavity of matching dimensions. Once assembled, holes are drilled through both pieces and hardwood pegs are driven into place. Over time, the wood fibres swell slightly, tightening the connection naturally. This method eliminates steel from the joint while producing a connection capable of supporting substantial loads. Outdoor benches, garden gates, and even small footbridges can benefit from similar approaches. The relationship between moisture movement and long-term structural health. One of the most important lessons from historic timber construction involves understanding how moisture travels through wood. Wood is a hygroscopic material, meaning it absorbs and releases water depending on environmental conditions. This constant exchange is normal and harmless when the wood is allowed to dry naturally. Problems arise when moisture becomes trapped. Steel fasteners frequently create pockets where evaporation is slowed. Rust then forms within those pockets, further obstructing airflow and sealing moisture inside the wood. Traditional carpentry methods were designed with this reality in mind. Joints were shaped so water could drain away rather than accumulate. Wooden pegs allowed moisture to pass through the joint without trapping it against metal surfaces. Covered bridges offer another example of moisture management. By shielding structural beams from direct rainfall, builders drastically reduced the amount of water entering the timber. Less moisture meant slower decay and longer structural life. The lesson is straightforward. Durability in timber structures depends less on brute strength and more on controlling the movement of water. Real-world restoration projects reveal the difference between wood and steel connections. Modern restoration projects often provide striking demonstrations of how different fastening methods age over time. When engineers dismantle historic timber structures for repair, they frequently discover that original wooden joints remain surprisingly solid. The surrounding wood may show minimal decay even after a century of service. In contrast, later modifications using steel hardware often reveal dark, softened wood surrounding the bolts. Rust stains spread outward from the metal core, marking the path of moisture intrusion. Restoration teams sometimes remove metal plates and replace them with wooden joinery precisely because the latter has proven more durable in outdoor conditions. These decisions are not driven by nostalgia. They are based on direct observation of how materials behave over decades. The conclusion reached by many preservation specialists is that compatibility matters more than raw material strength. When every component in a structure responds similarly to environmental changes, the system remains stable for far longer. The survivalist perspective on building structures meant to last generations. For survivalists and off-grid builders, the lessons from historic timber construction carry particular significance. Long-term resilience requires structures that can endure without constant replacement parts or specialized hardware. Steel bolts and screws often require industrial manufacturing processes that may not be readily available in a resource-limited future. Wooden joinery, on the other hand, relies primarily on tools and skills rather than manufactured components. A builder equipped with chisels, saws, and hardwood stock can create durable connections using materials found locally. This approach aligns closely with traditional craftsmanship, where knowledge and technique served as the primary engineering tools. Barns, storage sheds, and livestock shelters built using all-wood joinery can remain functional for generations with relatively simple maintenance. For those interested in preparedness and sustainable living, the historical record provides a powerful reminder that durability often comes from simplicity rather than technological complexity. Reconsidering the role of modern fasteners in 2026. None of this means steel fasteners should be abandoned entirely. They remain essential in many structural systems, particularly where steel interacts with steel or where controlled indoor environments prevent corrosion. However, when building outdoor timber structures intended to last decades or centuries, the automatic assumption that metal is superior deserves careful reconsideration. The 19th century philosophy of all-wood construction emerged not from technological limitations but from centuries of practical observation. Builders saw what lasted and what failed. Today, with modern knowledge of corrosion chemistry and moisture dynamics, those observations make even more sense. In many cases, the most durable solution is not the newest technology, but the oldest wisdom. Why does understanding these hidden weaknesses change how you see wooden structures? Once you understand how rust spreads inside timber joints, it becomes difficult to look at a wooden bridge or deck in the same way again. Every steel bolt represents a potential starting point for decay. Every nail hole becomes a miniature environment where moisture might linger longer than it would on open wood surfaces. Yet alongside that awareness comes a renewed appreciation for the ingenuity of historic builders. Long before corrosion science existed, they developed techniques that quietly solved the problem. Their methods remind us that durability often depends on respecting the natural behavior of materials rather than forcing incompatible ones together. For anyone fascinated by the intersection of history, engineering, and practical survival knowledge, this topic reveals how much wisdom remains hidden in traditional craftsmanship. If you enjoy exploring forgotten engineering ideas, historical construction methods, and the practical lessons buried in old technologies, make sure to subscribe to the channel and share this video with fellow history enthusiasts. The past still has a great deal to teach us, and every week we uncover another piece of knowledge that refuses to stay buried.